Good evening, everyone. My name is Saloni Vishwakarma, and I am a student at the International Institute of Professional Studies, DAVV Indore. I have been studying theory of computation for the past 2.5 months and have a keen interest in the subject. Today, I will be discussing some key concepts in the theory of computation and their applications. We will start by defining some basic concepts, then move on to discuss automata theory and its relevance in computing. I am excited to share this information with you today and look forward to our discussion. These are the table of contents. We have 10 questions and the last one is conclusion. So the first question is use the set of productions to show that each of these sentences is a valid sentence. First one is the happy hare runs. Second, the sleepy tortoise runs quickly. Third, the tortoise passes the hare. D. The sleepy hare passes the happy tortoise. This is the solution. A. The happy hare runs. Sentence noun phrase. Intransitive verb phrase noun phrase. Noun phrase is article adjective noun. Intransitive verb phrase which is intransitive verb. Article is the, adjective is happy, noun is here and the intransitive verb is runs. B. The happy tortoise runs quickly. Sentence. Sentence is noun phrase. Intransitive verb phrase noun phrase. Noun phrase is article. Intransitive verb phrase is intransitive verb adverb. Article is the. Adjective is sleepy. Noun is tortoise. Intransitive verb is runs. Adverb is quickly. The tortoise passes the hare. Sentence is noun phrase. Transitive verb phrase noun phrase. Noun phrase is article noun. Transitive verb phrase is transitive verb. Article is the. Noun is tortoise. Transitive verb passes and the noun is here. Same as for the D, the sleepy hare passes the happy tortoise. Sentence is noun phrase, transitive verb phrase, noun phrase. Noun phrase is article, adjective, noun. Transitive verb phrase is transitive verb. Article is the. The adjective is sleepy. The noun has here. Transitive verb is passes. Noun phrase is article, which is adjective noun. Article the. Adjective is happy and the noun is tortoise. This is a diagrammatic representation of the first part, the happy hare runs. This is for the second part. This is for the third part, the tortoise passes the hare. And this one was the last, the sleepy hare passes the happy tortoise. So the third question is part A. Construct a phrase structure grammar that generates all signed decimal numbers consisting of a sign either plus or minus, a non-negative integer, and a decimal fraction, that is either the empty string or a decimal point followed by a positive integer where initial zeros is an integer are allowed. Part B. Give the Backus-Naur form for this grammar. Part A. Phrase structure grammar. Sign decimal is sign non-negative integer, decimal fraction. Sign is plus and minus. Non-negative integer a digit and digit non-negative integer. Fourth one is decimal fraction, which is epsilon or positive integer. Positive, positive integer can be digit or digit positive integer. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. The epsilon. This is Backus-Naur form BNF. Sign decimal, sign non-negative integer decimal fraction sign. Non-negative integer equal to digit, digit non-negative integer. Decimal fraction is epsilon, positive integer. Positive integer equal to digit and digit positive integer. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Epsilon. The C part is give production rules in Backus-Naur form for an identifier if it can consist of one or more lowercase letters, at least three but no more six lowercase letters, 1 to 6 uppercase or lowercase letters beginning with an uppercase letter. Fourth, a lowercase letter followed by a digit or an underscore followed by 3 or 4 alphanumeric characters. Lower or uppercase letters are digits. This is the solution. First, identifier. This I clutter. Identifier I clutter. I clutter equals to A, B, C to Z. Second, identifier, which is I clutter. Third, which is also an identifier. And the fourth one, which is also an identifier. This is the solution for the given problem. Part D is give production rules in Backus-Naur form that generate all identifiers in the C programming language. In can, identifiers start with a letter or an underscore that is followed by one or more lowercase letters, uppercase letters, underscore and digits. Identifier, just letter OS, identifier symbol, letter OS equals to letter, symbol equals to letter OS digit, letter equals to I letter or U letter. I letter is A B C D to Z in lowercase and U letter is A B C D in uppercase. Digits is 0, 1, 2 up to 9. So the fourth question is give production rules in extended Backus-Naur form that generate all decimal numericals consisting of an optional sign, a non-negative integer and a decimal fraction, that is either the empty string or a decimal point followed by an optional positive integer, optionally preceded by some number of zeros. Numer Numerical equals to sign, non-zero digit, digit into decimal, sign or zero decimal. Sign equals to plus and minus. Non-zero digit is 1, 2 up to 9 and the digit is 0 or non-zero digit. Decimal equals to digit. The fifth question is give production rules in extended Backus-Naur form for identifiers in the C programming language. These are the some identifiers: letter OS, symbol, letter, I letter, U letter, and digit. Identifiers are letter OS symbol. Letter OS is letters. Symbol is equal to letter OS or digit. letter is equal to ike letter and uke letter. Ike letter equals to A, B, C up to Z in lowercase, and uke letter is A, B, C up to Z in uppercase. Digits are 0, 1, 2 up to 9. The sixth question is for each of these strings to determine whether it is generated by the grammar given for postfix notation. If it is find then steps used to generate the string. So these are some strings ABC multiply plus xy plus xy minus z into wxyz minus a and ade. These are the solution for the given strings. The seventh question is use Backus-Naur form to describe the syntax of expression in infix notation, where the set of operators and identifiers is a name, as in the BNF for postfix expression, but parentheses must surrounded expression being used as factors. For each of these strings, determine whether it is generated by the grammar for infix expression by it or not. If it is, find the steps used to generate the string. X plus Y plus Z, AB plus CD, m into n plus pt plus m minus n plus p minus q, m plus n into p minus q. This is the solution for the strings. First one is x plus y plus z, which is not generated. The eighth question is part A. Construct a finite automata to accept the set L of all string over 0 to 1 ending with 0, 1, 0. This is the diagrammatic representation of finite automata that accept L of all strings over 0 to 1 ending with 0, 1, 0. The part B is construct a pushdown automata to accept that set L of all string over 0 to 1 ending with 0, 1, 0. So the pushdown automata is a finite automata with extra memory called stack, which helps pushdown automata to recognize context-free languages. A pushdown automata can be defined as Q is the set of states, sigma is the set of input signals, L is the set of pushdown symbol which can be pushed and popped from stack, Q0 is the initial state, Z is the initial pushdown symbol which is initially present in stack, F is a set of final states. By applying these rules, we have this solution. The next question is construct a Turing machine to accept the set of L of all string over 0, 1 ending with 0, 1, 0. Firstly, a Turing machine is a mathematical model of computation describing an abstract machine that manipulates symbols on a strip of tap according to a table of rules. Despite the model's simplicity, it is capable of implementing any computer algorithm. The machine operates on a finite memory tab divided into discrete cells, each of which can hold a single symbol drawn from a finite set of symbols called the alphabet of the machine. It has a head that at any point in the machine operation it is positioned over one of these cells and a state selected from a finite set of states. The Turing machine was invented in 1936 by Alan Turing, who called it as a machine automatic machine. Turing machine in a review with this model, Turing was able to answer two equations in the negative. This is the diagrammatic representation of Turing machine that accept the set L of all string over 0 to 1. The ninth question is construct a Turing machine that accept the language 0, 1 plus 1, 0. This is the diagrammatic representation of Turing machine that accept the language 0, 1 into plus 1, 0. The 10th question is construct a push down automata A equivalent to the following CFG S 0 BB, B is 0S or 1S or 0. Test whether 010 to the power 4 is in NA. So this is the solution. States Q0 is the initial state, Q1 is state for handling 0 production, Q2 is state for handling 1 production, and Q3 state for handling the second 0 in the string. Q4 is accepting state. These are the transition rules. And in the last, testing the string for 0104. Initial configuration is Q0 is 0104Z. By applying transition rule based on the input strings, the string 0104 is accepted by the push down automata. Thank you for being here today. I hope you find this presentation informative and engaging.